describe some applications of microlocal sheaf theory. So one of them is this recent theorem of Vivek-Chendes. And one of them is maybe a bit older proof of non-displaceability. Okay, and then maybe I'll spend a little bit longer on mirror symmetry. All right, so if I have two knots, all right, they have two conormal tori. Right, call them lambda 1 and lambda 2, which are Legendrian tori in the cosphere bundle over the 3-sphere. The 3-sphere is can be framed, so this is S2 times S3. So here's the theorem. Suppose that lambda 1 and lambda 2 are Legendrian isotopic. Then, let me put it this way. Okay, S3 comma K1 is homeomorphic to S3 comma K2. I'm not sure the status of whether that homeomorphism can be taken to be orientation preserving. So the proof uses this Guillermo-Kashiwara-Shapira theorem. So first of all, we can assume that the isotopy between lambda 1 and lambda 2, it happens entirely inside of or over one hemisphere of the 3-sphere. So here's a cartoon picture 1 dimension down. So here's a 2-sphere instead of a 3-sphere. And instead of a knot, maybe we have a codimension 2 submanifold of that. And then over here is another one. And then in between, well, the isotopy in its, let's see, the isotopy of the conormals of these codimension 2 submanifolds, the projections will could be a little crazy, right? Could look like that, and then they'd settle down again to those 3 points on at the end of the isotopy. And meanwhile, maybe nothing is happening in the northern hemisphere. So according to Guillermo-Kashiwara-Shapira,
sorry, so are you still proving why we can assume they lie on?
Oh, I'm not proving that. I'm just saying it's safe to assume it.
That's just a fact, because the hemisphere is R3.
But making the isotopy uses all of S3. Why can we assume it? I mean, Vivek stated it for R3.
Oh. Okay.
The general position doesn't give this to you.
If you would have some example on the website that you can.
So I suppose that.
Wait, I'm confused, sorry, about the dimension of the front projection. So, oh, right, at intermediate times, they become codimension 1 thing. So
Right.
the space of the thing is codimension 0, etc.
Right, right. So so according to Kashiwara-Shapira, these categories will be equivalent. And let's see, so long as this isotopy leaves some point alone, these stock functors, this equivalence will commute with these stock functors. To the derived category of abelian groups. So these lambda sub I, they are the conormal varieties, conormal Legendrians of a Whitney stratification, simple Whitney stratification on the 3-sphere. So the categories themselves, they're just sheaves on S3 that are locally constant away from K and locally constant on K. So in particular, let's see, these stock functors, it's a stock at a point far away from the knot. The endomorphism group of this stock functor that stock functor at X, it's going to be well, in the language of last time, it would be the chain algebra on the loop space of the complement of the knot based at that base point. Which is reduces, in the case of a knot, to just the group ring. OK, so on account of Guillermo Kashiwara-Shapira, the fundamental groups of the complements of these knots are the same. So the group rings of the fundamental groups of the complements of these knots are the same. So it's a classic theorem of algebra.
Sorry, can we have an explanation of this?
Which one? Oh. It's the same explanation as on Wednesday. Let's see. So this the stock functor is represented by let's see, on a if I have a Whitney stratified space and I have an open stratum, which is a k-pi1 space, let's say, then the stock at a point in that open stratum will be represented by, well, I take the universal cover of the stratum containing X. And I look at the map to, OK, the stratum containing X, and then the inclusion. M. OK, I look at that composition, and I take the push forward with proper supports of just the constant sheaf on the universal cover. So this object represents this functor.
the stratum is just the complement.
Stratum is just the complement.
But sorry, but you ended up with the stalk being just, I mean, you map to D of Z, so just basically abelian groups. And so you forget the ring structure on the group ring?
It's the endomorphism ring of this functor, which is that ring. The functor itself is just the stalk, or Hom from
Okay, so,
yeah, this
so represented means that Homs into this object is the stalk functor.
from this object.
I see, and this is
So-
endomorphisms of the functor.
Yeah.
So why are Homs from this object? I mean, if I
Well,
try to do something simple.
There are, let's see, because push forward has an adjoint. This is an étale map. So the adjoint of the right adjoint of shriek push forward is shriek pull back. Shriek pull back along an étale map is regular pull back. We're pulling back to a contractible space, which is the same as pulling back to a point. That's maybe that'll do.
Can you write that?
Slowly or write it?
Yeah, let's see. So what do we have? We have a universal cover. We have a stratum.
Yeah, just pretend briefly that you're French.
We have a. I won't do the accent. We have a stratum in X, which is an open set, and we have a covering map, universal cover, and by assumption, this is contractible. And we have the constant sheaf on this universal cover.
And you should give this map a name and then write down the formula.
Let's call this composite F. Right, so claim one is that X is well, I guess I call it M. It's S3, and S is the complement of a knot. Well, the shriek push forward of F, of a sheaf capital F, on S tilde, space of maps from there into a sheaf G on X is the same as, well, more or less by definition of this upper shriek functor.
Why are you using lower shriek? I thought it was just the ordinary push forward.
No, it's going to be the proper push forward. So you want the direct sum of all the fibers instead of the direct product of all the fibers. Of all the points in the fiber, sorry. Well, and if F is locally a homeomorphism, then F upper shriek is the same as F upper star. So let's see, if capital F here is the constant sheaf on S tilde, well, homomorphisms from a constant sheaf, that's global sections. So this is global sections of S tilde with coefficients in this sheaf F upper star of G. And S tilde being contractible and F upper star G being locally constant, on S tilde, these are isomorphic to this is isomorphic to any stalk. So this step uses the constructibility of the sheaf G and kind of the characterization of locally constant sheaves as being sheaves that assign isomorphisms to any restriction map between contractible sets.
But isn't F lower shriek always the adjoint of F upper shriek?
Yes.
Sorry, the star. I
No.
should have said stars.
No.
No, that's the point.
No, but it is true when F is a local homeomorphism, locally on the
I
domain.
wanted to say lower star and upper star.
Upper star is the left adjoint of lower star. Well, the next step is just an appeal to some old theorems. Let's see, I didn't write their names down in my notes. So one of them is a 1950s theorem of algebra.
So now we know that it's represented by this object. Now we have to compute the homomorphisms of the object.
Yes.
So
Well, they are, let me just tell you why the fundamental group acts on this object. Because the fundamental group is the same as deck transformations. Deck transformations act on the universal cover. So they act on this constant sheaf on the universal cover. Well, so just an old theorem about group rings. And I wish I remembered who. Maybe, is there somebody named Higman, an old algebraist named Higman? Could be wrong. Says that, well, if a group is indicable throughout, well, it doesn't matter what it means, but it means that every finitely generated subgroup of G has a homomorphism to the real numbers, a non-zero homomorphism to the real numbers. Then the units in this group ring are just the units in the integers and the elements of the group. Well, it's not true for a lot of groups, but it's true for groups that are indicable throughout. And then a 1980s theorem, well, so this is true for knot groups. Knot groups are indicable throughout. Therefore, the fundamental groups of the complement of K1 and the complement of K2 are the same. Well, it's not enough to conclude that the knots are the same. To conclude that the knots are the same by, another classic theorem of knot theory, you need to know that the peripheral subgroups are the same. So about that, let me just say you can get at the peripheral subgroups it's the subgroup generated by longitude and meridian of the knot. So if I take a deleted tubular neighborhood of the knot, it's a torus. The fundamental group of that torus it determines a conjugacy class of subgroups in the fundamental group of the knot complement.
And such subgroup is a peripheral result.
Yes. Well, you can get at them by looking at the Morse groups along the knot. But sorry, in the sense of, or maybe you call them microlocal stalks, in the sense of Wednesday's talk. So
but you mean again as functors?
As functors, and now you look at how that Morse group functor talks to the stalk at X functor. So I think in this proof probably makes sense to a lot of people in this room in the language of partially wrapped Fukaya categories. So if I think there are two Lagrangians that generate the Fukaya category of the cotangent of S3 with called a stop, with a stop along the knot, or the conormal of the knot. So you have two objects that generate that. One of them is something transverse to the 3-sphere, and one of them is something transverse to the conormal of the knot. And that's more or less what this computation is in the language of Fukaya categories. Although the theme of Wednesday was how much you can do without.
What would you be taking then, and what object would you be taking?
Some Lagrangians in the.
Lagrangian of the fiber at infinity.
Some Lagrangian transverse to the fiber, or to the conormal bundle of the knot. Well, took longer than I expected. Let me skip Tamarkin. I'll skip. Although something, Tamarkin's proof of non-displaceability is pretty influential, but maybe I'll skip it.
Can you say what non-displaceability is?
It says that a non-displaceability result is a result that says that if you move a Lagrangian by Hamiltonian isotopy, it intersects. After a certain amount of time, it still intersects the original Lagrangian. So in 2008 and 2010, I was a postdoc at Northwestern, and I was talking to Bohan Fang and Melissa Liu, Derek Zaslow, and later on Nicolo Sibila, Rudat, about possibility of getting at HMS, or results akin to HMS, homological mirror symmetry, via microlocal sheaf theory. So, of course, microlocal sheaf theory doesn't have any holomorphic disks in it, so it's hard to say maybe what you mean by the A model. And there are probably other limitations to this approach. But we got a certain distance, and then Sheridan just proved homological mirror symmetry in all the examples that we had been thinking about. So if you ask me why I'm revisiting it in 2017, maybe I won't be able to tell you, but there have been some recent developments. So Nadler has taken up this idea of approaching homological mirror symmetry with sheaf theory, and some loose ends were settled by Mitka and Kuwagaki. There's some kind of ideas of Kuwagaki and Ike. But let me start with torque varieties. So I'll even write the definition of a torque variety on the board. So an algebraic torus, something isomorphic to C star to the n, if it acts on a variety, call it Y, with finitely many orbits, then it's called a torque variety. And kind of a fundamental result, basic result of toric geometry is that, there's a bijection. Between torus equivariant line bundles, let's say torus equivariant ample line bundles on Y, and lattice polytopes. In Rn, all right, so this torus contains a maximal compact subtorus, and this Rn will be the dual Lie algebra of that compact torus. Well, of a certain shape. Certain shape depending on Y. Right, so all of these polytopes in R2 have the same shape. So the left-hand side of that bijection is a category. And, well, right, given two line bundles, you can compute HOMs or X's between them. So, and those X groups have a computation in terms of the right-hand side due to de mesure. Here's a special case. call this bijectional. Send a line bundle L to a polytope delta L. So first of all, suppose that the polytope associated to L is contained in the polytope associated to M. Then the X group, well, the torus equivariant X group from L to M is concentrated in degree 0, where it's one-dimensional. Okay. You could take the curvature form of L and look at the moment map image. If the moment map is well defined up to translation, but if the line bundle is equivariant, you can pin down even the location in space.
You could also just take sections.
You could take
the T weights of sections.
Yes. So you could take the T weights of sections, or you could take the convex hull of the characters at the T fixed points. The T weights of sections, that's essentially this theorem.
Here X with subscript T, but then subscript.
Well, there's a torus action on Y, and these are equivariant line bundles. You can compute X in the category of coherent sheaves or in the category of equivariant coherent sheaves. That subscript means do it equivariantly.
I'm not sure I believe the statement in that direction. No.
Yeah, so if M is O of 100
Yes.
on P1, and L is O of 10 on P1, then there will be a lot of sections. So a lot of maps from O10 to O.
So why is that not a lot here?
So, say that again?
So why do you just have C? Why is it
Because
it's
one
torus.
given weight.
It's the one of the given weight.
for finding in weight. Okay. Oh, right, sorry. Yes, okay. Thanks.
Okay. So there are constructible sheaves on Rn with the same X pattern. So they're called costandard sheaves. So let me just write cost of delta. So this, if here's a polytope delta, then the costandard sheaf on it has it's constant on the interior of this polytope with rank 1 fibers, and 0 on the boundary and 0 beyond the boundary. And it's convenient to shift this by n, by the dimension of Rn. So this costandard sheaf, it's exactly the sheaf that represents the functor that evaluates a sheaf on the interior of this polytope. Well, and then shifts it. I guess shifts it in the opposite direction. So if I have one polytope contained in another, then I'll see the same Ext pattern. And Desmausure's full formula, well, maybe after some kind of Fourier transform, says that this is true for in general. So Ext I, torus equivariant Ext I from one line bundle to another, whether or not the two polytopes are contained in each other, is the same as the X group in the category of sheaves on Rn, one of these costandard sheaves against another. So if I have two polytopes whose moment map images overlap like this, two line bundles whose moment map images, whose moment polytopes overlap like this, then the right-hand side, this, is equal to the cohomology, ith cohomology of the intersection of these two polytopes relative to the orange stuff on the boundary. So I take the cohomology of this whole polytope, and I relative to part of the boundary. So Bandal, around 2005, Bandal, proved there's a full embedding of, well, coherent sheaves, maybe I better say perfect complexes, on Y into the category of sheaves on Rn that that extends this the bijection that I just erased. So in particular, that sends a line bundle to the costandard sheaf on a polytope and identifies the hums between them in this Desmausure style. Okay. Maybe. All right, so you have.
You basically proved it, assuming that you know that line bundle.
Yeah. If line bundles, yeah, that's right. I think they don't always for a singular variety, but or okay. Well, so this is called the coherent constructible correspondence. So ample line bundles on Y, they become convex polytopes. General line bundles become what Harshon and Treumann call twisted polytopes. Well, the sheaf, the support will look something like that, with weird boundary conditions and something weird happening at that vertex of the bow tie. Yeah, so some sequence of polytopes like that, and you can kind of continue it beyond the point where they're still polytopes. Okay, you could change the equivariant structure. That amounts to translating the polytope by a lattice vector. Could forget the equivariant structure. That corresponds to pushing push a sheaf forward along the map from Rn to Rn mod Zn. Which I guess maybe that's actually what Bondel proved, was this non-equivariant version. Let's see, you can translate a polytope, you could, or a sheaf. You could also dilate it. So you could dilate by, let's say, P. This corresponds to pullback by kind of toric version of Frobenius. Which raises every coefficient of the open orbit by P. Pull back by a toric blowup. Corresponds to doing nothing. You could tensor product of two sheaves. That corresponds to, well, Rn is a group. So it's convolution of sheaves using the group structure. On Rn. Okay. Well, it's fun to think about what one thing on the coherent side means on the constructible side. Something that is not addressed by Bondel's construction, which originally was some kind of weird argument thinking about, weird and cool argument thinking about push forward by this toric Frobenius map. Is what is the image of this full embedding? Okay. So that's a question that we mostly answered, partly answered anyway. So using the language of microlocal sheaf theory, that there exists a Legendrian in this torus, in the conormal of this torus, in the cosphere bundle over this torus, such that well, and its pullback under the universal cover, which I'll just write with a lambda y with a tilde, such that this embedding well, it factors through this category of sheaves of support in lambda sub y. And in fact, in the equivariant setting is equivalent to that category of sheaves. Let's see the same thing. Oh, if y is smooth. So, a recent theorem. Kuwagaki and Mitke-Weintraub independently. Same thing holds non-equivariantly. As long as y is smooth. So I'm going to tell you what this lambda y is. So first of all, there's a formula for it. Oh, okay, first of all, where does it live? It lives in the cosphere bundle over this Rn mod Zn. This it's not just any torus. This is the dual torus. Dual compact torus to the torus acting on y. So the tangent space to a point on this torus, that's the space where moment polytopes live. The cotangent space is the space where the fan of the torque variety lives. Well, I guess some kind of large sphere inside of that fan. So the fan associated to y lives here. So the formula for this lambda y is in terms of that fan, lambda y, well, okay, every cone in the fan associated to y, it has a corresponding subgroup of t hat. Called sigma perp, just a subgroup of this dual torus, compact subgroup of this compact commutative group. And lambda y is the union over all these cones of sigma perp times sigma. I think it works out under our conventions to be minus sigma. And I guess I'm looking at the cosphere bundle instead of the cotangent bundle, so it's the boundary of that cone sigma. Okay, so for example, say y is P2. Then lambda, so the fan of P2 looks like that. And this lambda y, well, it's embedded in a two-dimensional torus times a circle as a Legendrian. And it looks like this. This recipe, it makes sense also when y is a orbifold, a toric orbifold, then this subgroup might not be connected. So if you introduce some kind of orbifoldness along one of the toric lines in P2.
Can you explain again how you get to this link here?
Yeah, this fan, maybe this cone in the fan, the boundary is this in this picture. This ray here, the perpendicular, the sigma perp of this two-dimensional cone is the point subgroup.
That's the whole thing.
Well, we take the product with, let's see, where is the projection to the base here? It's not really visible. In the base, if here's a two-dimensional torus, it's a little bit less clear what I might have screwed that up. Probably this one should go down. Okay. There should be at least one triangle where they're all pointing in. Okay. Well, so this whole orange circle, it's the entire co-circle above 1 point, and then these remaining white circles kind of spread out around the two-dimensional torus like this. I could introduce some orbifoldness and put in like another chord in this graph.
We call weighted P2.
Weighted P2 with one whole toric line, T-stable line, which has been sort of divided by 2, or divided by the number of chords that I would draw there. Or look at P3. It's a little bit harder to draw how all of these figures fit together, but now there are at least, well, there are 4 two-dimensional tori in this lambda sub y, corresponding to the 4 open cones in the fan of P3. And then there are 6 Legendrian tubes corresponding to the 6 two-dimensional cones in the fan of P3. And there are, well, I didn't draw one of them. One of them is behind this picture. And there are 4 kind of triangles, Legendrian triangles, corresponding to the 4 rays in the fan of P3. And it's hard to maybe draw all these pieces attached to each other. But near each, so there's an additional tube and 2 additional triangles behind this picture. And in the neighborhood of this torus, it's you see, well, the link of it looks like this picture. Okay, so this, if you, let me erase that green line. Yeah.
Well, I mean, if you draw the fan for weighted P2, why is there an extra?
Oh, I made a mistake. I made a mistake. For the weighted P2 that I was thinking of, which I think the picture that I really wanted was this. I'm not sure I could. Let's see. So the fan of this weighted P2, I think I want an entire.
It's like P2 Treumann in terms of weights.
So I don't actually know what is meant by weighted PN, but it's some. I think the best. I think it's okay.
So it's not the one you can
So this is the same fan. The same fan is for P2, and I think, though I might have gotten this wrong. I think the kind of stacky structure on that fan are those. Those ones. Well, so this, it's easy to see that this picture has the homotopy type of the curve x plus y plus 1 over xy equals 1 inside of C star times C star. Maybe it's a little harder to see that this has the homotopy type of x plus y plus z plus 1 over xyz equals 1 inside of C star times C star times C star. So that's not a coincidence. It's a theorem of Helder-Radat, Nicola Sibila, Zaslow, and myself. Yes, so suppose Y is a toric orbifold, that it's smooth, and that its course space is projective. And then let f be some Laurent polynomial on the complexified torus, dual to the torus acting on y, whose Newton polytope is the convex hull of the distinguished generators, giving the stacky structure of rays, giving the fan of y its stacky structure. Well, okay. So for example, those green dots, although, and suppose that it's generic with this property. All right, then. This Legendrian, lambda y, is embeds as a deformation retract into the hypersurface cut out by this polynomial. By the way, I don't know whether it's possible to remove that coarse space is projective condition. It's used to it's used to construct some degeneration of this and rebuild it as a Kato Nakayama space, and then lambda y is more or less obviously a subset of that Kato Nakayama space. Okay, that's the theorem. So by virtue of being a Legendrian in a co-sphere bundle, this lambda sub y, it carries a sheaf of categories. Yes, it's the Legendrian version of lambda y. So it carries a sheaf of categories called the Kashiwara-Shapira sheaf.
Can I ask you?
Yeah.
Shouldn't the dimension of lambda y be half of the real dimension of F inverse 0?
Yes. So for example,
Worked out like that? Ah, yeah, okay, sorry.
so this sheaf, really it's defined by Kashiwara and Shapira in their book as a pre-sheaf first. A pre-sheaf on directly on the co-sphere bundle. Well, okay. So if lambda is a Legendrian in the co-sphere bundle of M, and then there's a pre-sheaf defined directly on this co-sphere bundle by the formula, well, C of U, some open set, oh, not C. This pre-sheaf associated to U is the quotient of lambda union the complement of U by just the complement of U. Well, so
What if the complement of U isn't Lagrangian?
it's not. It's never Lagrangian, but it is coisotropic. So the complement of U is a big set. So both the numerator and the denominator of this quotient are very big categories of like all sheaves on M. With only some condition imposed close to, well, only some condition imposed inside of U. Well, so then this KS ought to be the sheafification of this pre-sheaf. So here's some announced but not written down properties of this sheaf of categories. So in this case, so I take the global sections of this pre-sheaf of categories on lambda y, on the whole Legendrian associated to y, I ought to get perfect complexes on, or maybe all quasi-coherent sheaves on the formal neighborhood of the boundary of y, the kind of union of the canonical toric divisor in y inside of all of y. If I sheafify it, I take global sections, I ought to get perfect complexes just on the boundary of y. So I'm not sure how much of this is in the work of Ike and Kuwagaki already, but Ike and Kuwagaki, well, they're thinking along similar lines. I don't know if I should attach their names to it. Let's see. So what's the significance of this kind of mirror symmetrically? So this hypersurface is a Weinstein manifold. So hopefully this lambda sub y is a, if this is a skeleton of this Weinstein manifold, then Kontsevich conjectured, maybe Kanatra, Shinde, and Pardon are working on proving it. But this lambda y carries a sheaf of Fukaya categories. Whose global sections would be the Fukaya category of F inverse of 0. Maybe in the way that I'm formulating it, the Fukaya category of compact Lagrangians. And well, so if this is the same sheaf, and this theorem is a kind of homological mirror symmetry theorem at the so-called large volume, large complex structure limit. Okay, but I guess I'll stop there.